Ever wish you could just cut through all the noise, get straight to the important stuff on complex tech without feeling like you're drowning?
Yeah, information overload is real.
Exactly. Well, that's what we're aiming for today. We're doing a deep dive into something pretty fascinating. The AMD FPGA display controller.
Right. And it's important to say up front, this isn't like one specific chip you buy off a shelf.
Good point.
It's really more of a capability, a very powerful and flexible one.
Okay, a capability.
Uh-huh.
And this comes from where?
Well, it kind of emerges from bringing together three distinct areas. You've got FPGA's field programmable gate arrays.
Mm-hmm.
Then you have the demands of modern cutting-edge display controllers. And finally, AMD's own high-performance computing stuff, which, got massively bigger after they bought Xilinx.
It's the Xilinx acquisition. That was huge, wasn't it? Around, what, $49, $50 billion?
Yeah, something like that. A massive deal.
So our mission today is really to unpack the architecture and how this capability is actually used, right, in the real world.
Exactly. We want to show its role in some really advanced industries and why it's so valuable. Things like its flexibility for custom video pipelines, the low latency processing, which is critical.
Deterministic low latency, you meant.
Yes, deterministic, that's key. Predictable. And also the strategic edge it gives in markets where, adaptability and reliability, long product life, that stuff really matters.
Okay. So we're aiming for those aha moments, connecting this complex tech to, real-world impact, how it shapes the future of visual stuff, data-driven applications. Let's get into it.
Sound good?
So to really get a handle on this AMD FPGA display controller capability, we probably need to break down the pieces first. Let's start with FPGAs themselves. What are they, basically?
Right. So an FPGA is a type of semiconductor chip, but unlike, say, an ASIC, which does one fixed thing, or a CPU that runs software instructions, an FPGA's hardware, its actual circuitry, can be reprogrammed by the user after it's been manufactured, in the field.
So like a silicon chameleon. You said that earlier. I like that. It can change its spots.
Yeah, exactly. A silicon chameleon. And that ability comes from its internal structure. Think of it like a grid.
Oh.
The core elements are these configurable logic blocks, or CLBs. These are the basic programmable units. Inside them, you have lookup tables. Think of them as tiny programmable truth tables and flip-flops for storing state, like memory bits.
And there are thousands of these.
Oh yeah, thousands, tens of thousands, even millions on the big ones. And you connect them together using this huge network of programmable wires and switches, the programmable interconnects. That's how you build your custom digital circuits.
But it's not just a sea of generic blocks, right? Modern FPGAs have specialized bits, too, for common tasks.
Absolutely. That's crucial for efficiency. You get these hardened, dedicated blocks baked into the silicon. Things like block RAM or BRAM and Ultra RAM, really fast on-chip memory. Essential for video stuff like frame buffers or line buffers. Then you have DSP slices, digital signal processing blocks. These are like dedicated math engines, hardware calculators for common operations in image processing like filtering or maybe color adjustments. Way faster and more power efficient than building those math functions from scratch using the general logic blocks.
Gotcha. So specialized hardware for the heavy lifting.
Right. And you also get high-speed transceivers, often called SerDes. These handle the really fast data communication needed for interfaces like PCI Express, high-speed Ethernet, HDMI, DisplayPort, moving gigabits per second.
And clock management, too, I guess. Timing must be critical.
Oh, definitely. Dedicated clock management blocks, PLLs, and DLLs make sure everything runs with precise, stable timing signals.
Okay, this is where it gets really interesting for me, the parallelism. You said unlike a CPU.
Right. A CPU fundamentally runs instructions one after another, maybe with some clever tricks. But an FPGA, you can configure it to have literally thousands of independent processing pipelines running at the exact same time. Each task gets its own dedicated slice of hardware, all operating in parallel. That's why FPGAs are just killer for tasks like processing every single pixel in a video frame simultaneously. It's true hardware parallelism.
Which leads us nicely into the display controller part. That parallel power must be exactly what's needed.
It really is. The display controller's job is basically to take that digital image data, usually from memory, and generate these super precise signals needed to drive an actual physical screen. It's the translator between the computer's idea of an image and the photons hitting your eyes.
And that translation involves several steps, like a pipeline.
Yep, a video pipeline. It
Uh-huh.
starts with things like image compositing, taking different layers, maybe a background, a video window, your mouse cursor, graphics overlays, and
Yep.
blending them together correctly, handling transparency with alpha blending.
Okay. Layers combined, then what?
Color management, making sure the colors are accurate. This involves converting between different color spaces, like maybe YCBCR from a video source to the RGB your monitor uses,
Hmm.
and technical stuff like degamma and regamma to ensure the brightness levels look right.
Accuracy is key there.
Definitely. Then comes timing generation. This is super critical, generating the precise horizontal sync pulses, the vertical sync pulses, all driven by a master pixel clock. This defines the resolution, the refresh rate, like 1920 by 1080 at 60 hertz. It has to be perfect.
Right. Or the screen just won't work.
Exactly. And finally, interface encoding. Taking all that pixel data and the timing signals and encoding them into the specific electrical format for the cable, like TMDS for HDMI or the signaling for DisplayPort. Often it also involves reading EDI data from the monitor, extended display identification data. It's how the source device, like the FPGA, asks the display, hey, what resolutions and refresh rates can you handle? So it can output a compatible signal.
Clever. Okay, so now let's bring in that big industry shift.
Mm.
The AMD Yellings deal. You mentioned it earlier, closing in early 2022 for around $50 billion. This wasn't just consolidation, was it?
No, not at all. It felt very strategic. AMD's leadership explicitly said the goal was to create the industry's high-performance and adaptive computing leader.
Adaptive computing. That sounds like FPGAs.
Precisely. The core idea was to combine AMD's strength in CPUs and GPUs with Xilinx's leadership in FPGAs and these things called adaptive SoCs. The vision is what we call heterogeneous computing, meaning a single platform where CPUs, GPUs, FPGAs, and even specialized AI engines all work together seamlessly. Each part handles the tasks it's best at. It's about using the right tool for the right job, all integrated.
So this flexible FPGA tech we're talking about, it's now a core part of the AMD portfolio, benefiting from AMD's graphics know-how and Xilinx's low-latency hardware background.
That's exactly it. And it massively expands AMD's potential market, their total addressable market, or TAM.
Yeah.
They estimated it at something like $135 billion. Yeah, targeting really high growth areas. Data centers, 5G, automotive, industrial, aerospace, and defense. Places where this kind of adaptive high-performance computing is increasingly crucial.
Okay, that sets the stage. Let's dive deeper now into the AMD FPGA video pipeline itself.
Yeah.
You mentioned this hybrid approach using both flexible soft logic and efficient hardened IP. How does that actually work in a design?
Right, so the hybrid approach is key. You use the hardened IP blocks, the pre-built, optimized silicon for the standard, really performance-hungry stuff.
Oh, explain.
Like using the on-chip RAM or ultra-RAM for frame buffers, using the DSP slices for the heavy math and scaling algorithms or color space conversions, using the dedicated clock management blocks, the PLLs for generating pixel clocks, and using those high-speed transceivers for the physical layer of, say, HDMI or DisplayPort. These are just way more efficient in terms of speed and power than trying to build them out of generic logic.
Okay, so the hard blocks handle the grunt work. What about the soft logic, the programmable fabric?
That's where the customization comes in. That's where you implement your unique control logic, maybe specific blending algorithms your product needs, the state machines that control the exact timing generation, or any proprietary image processing sauce that makes your product special. It gives you that flexibility.
And because it's an FPGA, this whole pipeline runs in parallel with very low predictable latency.
Exactly. Deep pipelining is natural in FPGAs. Pixel data flows through this chain of custom hardware stages, often with a new pixel entering the pipeline every clock cycle. And the latency is deterministic. You know exactly how long it takes, which is critical for real-time interaction.
Well, let's walk through those stages again, but specifically in the FPGA context. It starts with ingestion and capture.
Right. And FPGAs excel here because their I/O pins are so flexible, you can configure them for almost anything. Use the hardened transceivers for standard inputs like HDMI or DisplayPort. Or use the general-purpose I/O pins to connect directly to an image sensor using protocols like MIPI CSI2, which is common in cameras. It's that any-to-any connectivity.
Very versatile. Then the in-pipeline processing.
Yeah, the pixel data streams through your custom hardware pipeline. This could involve blocks for color space conversion, say YCDCR to RGB, blocks for scaling, making the image bigger or smaller or deinterlacing old video formats, Image enhancement too, maybe noise reduction, sharpening, or even running something like a Sobel filter using the DSP slices to detect edges.
And if you need to store more data, like full frames for complex processing or high resolutions.
That's where memory and frame buffering comes in. The on-chip RAM Multiram is great for fast, low-latency line buffers or small FIFOs. But for large frame buffers, especially for 4K or 8K video, FPGAs have hardened DDR memory controllers to interface with external DRAM chips, giving you that large capacity.
Okay. And finally, getting the signal out, composition and output generation.
Yep. You'll typically have a custom block built in soft logic that generates the precise H-sync, V-sync, and other timing signals using the FPGA's clock management resources. This module takes the final process pixel data and feeds it to an output block. Often, this output block is itself a piece of licensed IP.
Intellectual property cores, right? Let's talk about those. They seem crucial.
Oh, absolutely essential. Nobody builds these complex systems entirely from scratch anymore. It's just too time-consuming and risky. Designers rely heavily on pre-designed, pre-verified IP cores that implement specific functions. It's like using prefabricated components.
And AMD provides a lot of these themselves, especially after acquiring Xilinx.
They do. They have an extensive catalog. For example, a complete DisplayPort subsystem IP core that handles DisplayPort 1.4, supporting features up to 8K resolution. Same for HDMI and HDMI subsystem IP for HDMI 2.1, supporting the latest high speeds, 8K 60, dynamic HDR, even content protection like HDCP.
And something called a video PHY controller.
Right, the VPHY. That's the piece that connects the logical MS layer of DisplayPort or HDMI to the actual physical high-speed transceivers on the FPGA chip. It bridges that gap.
But it's not just AMD's IP. There's a whole ecosystem.
Definitely. A very healthy third-party ecosystem exists. Companies like Integra, Digital Blocks, Bytech, MRA Digital. They offer specialized IP cores, sometimes alternative, sometimes complementary things that AMD doesn't offer.
And tools like Vivado IP Integrator help put all these pieces together, like snapping Lego bricks.
Pretty much. IP Integrator lets you visually connect these IP blocks using standard interfaces, typically AXI these days. It really shifts the focus from low-level wiring to designing the overall system architecture. It's a huge productivity booster.
Okay, let's talk architecture examples. You mentioned Zinc UltraScale plus EV and Versal AI Edge. How do they differ in their approach to video?
They represent a really interesting evolution. Zinc UltraScale plus EV is what AMD calls an MP-SUSI multiprocessor system on chip. Its key idea is tightly coupling traditional ARM processor cores, the processing system or PS, with the flexible FPGA fabric, the programmable logic or PL.
And for video, its standout feature is
a hardened video codec unit, the VCU. This is dedicated hardware for efficiently encoding and decoding video streams using standards like H.264 and H.265, supporting up to 4K at 60 frames per second, even multiple streams.
so perfect for things where you need video decompression like streaming, conferencing, surveillance cameras.
Exactly. It's optimized for that. It also has other hardened video-related blocks like a DisplayPort 1.2 controller and even a small ARM Mali GPU for basic graphics.
Okay, now contrast that with Versal AI Edge. That
Yeah.
sounds like the next generation.
It is. Versal is AMD's ACCAP Adaptive Compute Acceleration Platform. It's a more advanced heterogeneous architecture. It integrates scalar engines like ARM CPUs, adaptable engines, the FPGA fabric, and intelligent engines. These are arrays of AI and DSP processors, all connected by a high bandwidth network on chip.
More ingredients in the mix. What's new for video here?
Well, it has an enhanced VCU, even better quality, supporting 12-bit color depth. But the really big news, I think, is the inclusion of a hardened image signal processor, or ISP.
An ISP, like in a camera chip.
Exactly. Dedicated hardware for all that front-end camera processing, demosaicing raw sensor data, noise reduction, handling high dynamic range, HDR. By hardening this, it frees up the programmable logic for other custom tasks.
That's a significant step. It makes the chip more of an end-to-end vision processing solution.
Precisely. Versal AI Edge is aimed at really complex applications where you need to sense the world with cameras, process that data intelligently using the FPGA fabric and AI engines, and then display the results all on one chip very efficiently. Think advanced automotive driver assistance, medical robotics, smart city cameras.
So it also has hardened display outputs.
Yes, hardened DisplayPort 1.4 support, native interfaces for MIPI CPHY sensors, and those powerful AI engines for running machine learning models right there on the edge. It's a much more integrated platform for sense process display, like you said.
Okay, that makes sense. Let's zoom out again to the big picture. When you're deciding what hardware to use for a display-heavy task, how do FPGAs stack up against the main alternatives, like GPUs and ASICs?
That's the critical system design question, isn't it? Choosing the right tool. Let's compare FPGA versus GPU first.
Okay. Both are parallel, but differently.
Right. GPUs excel at SIMD single instruction, multiple data, great for rendering thousands of polygons with the same shader or applying the same filter to a whole image. FPGAs offer true, fine-grained task parallelism. You can build completely different independent processing pipelines that run simultaneously.
And the big difference for real-time stuff is latency.
Absolutely. This is often the deciding factor. FPGAs give you very low latency, often in the microseconds or even nanoseconds. And crucially, it's deterministic predictable. GPUs operate on whole frames. There's overhead transferring data back and forth to the GPU memory using drivers. The latency is much higher, typically milliseconds, and it can vary.
So for something like robotic surgery or live broadcasting, where any noticeable delay is unacceptable.
FPGAs are often the only choice. GPUs just introduce too much unpredictable lag.
What about power and I/O?
For a specific well-defined task, FPGAs can be significantly more power efficient because you're only powering the logic you actually use. GPUs have large general-purpose processing arrays, and I/O flexibility is a huge win for FPGAs. You can configure their pins for almost any digital interface imaginable, connect directly to sensors, legacy buses, custom links. GPUs usually have fixed I/O like DisplayPort, HDMI, and PCIe.
But the downside for FPGAs is development complexity.
Traditionally, yes. GPUs have mature software ecosystems like CDA and OpenCL, which are relatively accessible to software developers. FPGA design requires specialized hardware description language, HDL skills like Verilog or VHDL.
Well,
Tools like high-level synthesis, HLS, which let you write C or C++ code and automatically generate HDL, are making FPGA development much more accessible to software folks. It's lowering the barrier.
okay, interesting trade-offs. Now, FPGA versus ASIC, application-specific integrated circuit.
Right. Here are the comparison shifts. ASICs are custom-designed chips, fixed function. Their biggest advantage is performance and power efficiency for a specific task. They are optimized down to the last transistor.
But they're inflexible.
Totally inflexible. Once an ASIC is manufactured, its function is set in stone. No bug fixes, no upgrades, no adapting to new standards without designing a whole new chip. FPGAs, being reprogrammable, offer immense flexibility. You can fix bugs in the field, add features, adapt to changing requirements. This drastically cuts down time to market weeks or months for an FPGA design versus potentially years for an ASIC.
And the cost is the other big factor.
Huge factor. ASICs have incredibly high upfront costs, the non-recurring engineering or NRE, mask sets, design tools, verification. It can easily run into millions, even tens of millions of dollars. FPGAs have essentially zero NRE cost related to chip manufacturing.
But the individual FPGA chips are more expensive than ASICs.
Yes, significantly. Once you've paid the huge NRE for an ASIC, the cost per chip in high volume is very low. FPGAs have a higher per unit cost, so there's a crossover point.
Where FPGAs make sense for lower volumes and ASICs for mass production.
Exactly. If you're making millions of widgets, like in a smartphone, an ASIC is usually the way to go. But if you're making thousands or even tens or hundreds of thousands of a specialized piece of equipment, or if your standards might change, the FPGA's lower NRE and flexibility often win out. Typically, that volume crossover is somewhere below, say, a few 100,000 units, but it depends heavily on the specific chips and application.
So FPGAs hit this Goldilocks zone, better latency and predictability than GPUs, more flexibility and lower NRE than ASICs.
That's a great way to put it. They're just right for a specific but very important set of applications, especially in markets needing real-time performance, custom interfaces, reliability, and maybe moderate volumes.
Which brings us to those application domains. You mentioned that sense process display idea. Where do we see FPGAs really shining?
Okay, let's look at a few. Professional AV and broadcasting is a big one. Image quality and low latency are paramount. FPGAs are inside live production switchers, handling multiple 4K or 8K streams, doing effects, compositing all with virtually zero delay.
Like for live sports.
Exactly. Also in video over IP gateways, using standards like SMPTE ST2110 to send uncompressed video over networks. High-end broadcast cameras often use FPGAs for the entire image pipeline right behind the sensor. And things like high-end projectors for geometric correction, warping, edge blending.
Makes sense. What about automotive? You mentioned that.
Yeah, cars are becoming incredibly complex electronic systems. FPGAs are key for digital cockpits, driving multiple high-resolution displays, bridging different interface types. Critically, in ADAS advanced driver assistance
The
systems,
safety features.
right. FPGAs perform real-time sensor fusion, combining data from cameras, radar, LiDAR, and run AI algorithms for object detection. They can then generate graphical overlays onto the driver's display or heads-up display with minimal deterministic latency. That's vital for safety. Also for things like e-mirrors or surround view systems, stitching camera feeds together instantly.
Imperceptible latency is key there.
Absolutely. Then there's medical imaging, huge area. Quality, accuracy, real-time performance are literally life-critical. Think surgical endoscopy FPGAs process the images from the tiny camera in real time, doing enhancement, maybe overlaying information, driving the surgeon's display with zero lag.
Wow.
Ultrasound systems use the massive parallelism of FPGAs for beamforming, which allows for very high frame rates and better image quality. And in big diagnostic machines like MRI, CT, PET scanners, FPGAs are often used to accelerate the complex image reconstruction algorithms.
And finally, aerospace and defense, AMD.
Yep. This sector demands extreme reliability, often radiation tolerance for space, security, and very long product life cycles because systems are deployed for decades. FPGAs fit well. Avionics displays in cockpits use them for processing sensor data and drawing symbology.
Like the artificial horizon and flight data.
Exactly. Radar and electronic warfare systems rely heavily on FPGAs for real-time signal processing, analyzing vast amounts of data very quickly to detect and track targets. Simulation and training systems use them for realistic, low-latency visuals. And in satellites, reconfigurable FPGAs allow missions to be updated or hardware repurposed even after launch, which is incredible.
Okay, so we have this incredibly powerful and flexible hardware. How do engineers actually build systems with it? What does the development ecosystem look like?
It's quite a sophisticated ecosystem, really blending hardware and software skills. The traditional way is using hardware description languages, or HDLs.
Verilog and VHDL.
Those are the main ones. They let you describe the hardware circuit in minute detail, gives you full control, but it requires deep digital design expertise and can be time-consuming.
So what are the alternatives?
Well, high-level synthesis, HLS, which we touched on, this is a game changer. You write your algorithm in C, C++, or System C, and the HLS tool automatically converts it into HDL code for the FPGA. This makes designers much more productive, especially for complex algorithms like image processing filters or compression math.
So more accessible to software engineers.
Definitely. There's also model-based design. Using tools like MATLAB and Simulink, often with AMD's Vitis Model Composer add-on, allows engineers to design and simulate systems graphically and then automatically generate the HDL code, popular in areas like signal processing and control systems.
But you said IP-based design is dominant now.
Yes, for building large systems, it really is. Using graphical tools like the Vivado IP integrator, you select pre-built, pre-verified IP cores like an HDMI receiver, a DDR memory controller, maybe a processor core from a library, and then you graphically connect them together using standard bus interfaces like AXI.
So you're focusing more on the system architecture.
Exactly. You're integrating these complex building blocks rather than designing every single gate yourself. It's much faster and less error-prone for complex designs.
And AMD provides the tools for all this, Vivado and Vitis.
Right. Vivado Design Suite is the main environment for the hardware-centric flow. It handles everything from writing or importing your HDL or HLS code through synthesis, translating it to logic gates, implementation, placing those gates onto the FPGA fabric and routing the connections, all the way to generating the final bit stream file that actually programs the FPGA. It includes IP integrator and the HLS tools.
Okay, that's the hardware side. What about Vitis?
Vitis is designed to bridge the hardware-software gap, especially for those heterogeneous platforms like Zinc and Versal that have both processors and programmable logic. It allows software developers to work in familiar environments like C++ or using frameworks like OpenCL.
How does it work?
Vitis essentially helps you partition your application between the software running on the ARM processors and hardware accelerators implemented in the FPGA logic. It provides libraries optimized for the FPGA hardware and handles the complex communication and data movement between the processor and the FPGA fabric, often over that AXI bus we mentioned. It makes leveraging hardware acceleration much easier for software teams.
That sounds powerful, but also complex. Getting all these hardware and software pieces working together correctly, meeting timing, that must be a huge challenge. Verification.
Oh, verification is a massive part of FPGA design. It's often where most of the engineering effort goes. It's not just about checking if the logic is functionally correct, but also ensuring it meets all the timing requirements that signals get where they need to go within the allocated clock cycle. Achieving timing closure can be really tough, especially on large, fast designs.
Chuckles slightly. Yeah, I've heard engineers talk about time enclosure like it's a mythical beast.
It sometimes feels like it. You need rigorous methodologies, things like constrained random testing, where you use tools to generate millions of random but valid input patterns to try and find unexpected bugs or corner cases. Functional coverage is used to track which parts of your design logic have actually been tested by your simulation test bench.
So you know you haven't missed anything crucial.
Hopefully. And complex projects often use standardized verification frameworks like UVM, the Universal Verification Methodology, to build reusable and robust test environments. And for systems with processors, that hardware-software co-design aspect is critical, making sure the software drivers correctly control the hardware accelerators and that data moves between them efficiently and without corruption. Tools like Vitis really help streamline this co-verification process.
Okay, so wrapping things up. We've seen the AMD FPGA display controller isn't just one thing, but this powerful capability built on reconfigurable hardware, advanced display tech, and that whole heterogeneous computing idea from the AMD Xilinx merger.
Right, and its core value really comes down to that unique combination. Incredible I/O flexibility to connect to almost anything, that deterministic low-latency processing, which is vital for real-time, and the ability to reconfigure it in the field.
We saw how it acts as this integrated sense process display engine in really demanding fields, broadcasting, automotive, medical, aerospace, and the evolution from Zinc, with its hardened video codec, to Versal, adding hardened ISPs and AI engines, shows a clear path towards blending ASIC-like efficiency with FPGA flexibility.
Exactly. It solidifies that Goldilocks zone for FPGAs, better deterministic latency than GPUs, way more flexible and cheaper upfront than ASICs for many applications.
So looking ahead, what's the trajectory for this technology?
I think we'll see even deeper integration of AI. Imagine real-time video analytics happening right inside the display pipeline, things like content-aware encoding, automatically adjusting compression based on what's in the scene, or intelligent image enhancement that understands the content.
Making the visual smarter.
Yeah. Also, higher levels of abstraction in the design tools, making it easier for software engineers to use FPGAs, maybe through Python frameworks, or even AI-assisted tools helping with the hardware design itself. Lowering that barrier to entry is key.
And adapting to new standards. FPGAs seem perfect for that.
Absolutely. New display standards like DisplayPort 2.x, new video codecs like AV1 FPGAs can be reprogrammed to support these much faster than waiting for new ASICs. That's a huge advantage. It really points to the continued rise of these heterogeneous, adaptive platforms like Versal ACK as the winning strategy for complex systems.
Combining the best of CPUs, programmable logic, and dedicated accelerators.
That's the future, I think.
So a final thought for our listeners, as you look at all the screens in your life, maybe pause and think, how might this hidden power of adaptive computing, these FPGAs, transform not just what we see, but maybe how we interact with and understand our visual world in the coming years?
Yeah, it feels like intelligence and adaptability are being woven right into the fabric of how we experience visual information. It's really just the beginning.